Hello, everyone. It's a true honor and privilege to have this opportunity to give a plenary at VTC, even virtually. I'd like to thank the organizers, Abbas and Layosh, for inviting me to give this talk. Of course, I was very much looking forward to seeing you all in person in Victoria, but very thankful to everyone involved for giving us an opportunity to meet and exchange ideas, even under these new circumstances. Before I begin, I'd like to wish everyone in the community and their families lots of health, and wish us all to be able to meet again soon in person. Today, we live in a digital world with extraordinary amounts of data being generated on a daily basis. What I'd like to share with you today are some ideas we and many others have been working on to acquire and process signals using much less resources than what is used today by combining ideas of signal processing and model-based deep learning. We'll try to show that this leads to new ways of sensing information, to interesting new technologies that can have an impact on various applications in radar and communication systems, as well as applications beyond engineering on science and medicine. So data today is being generated at exponentially growing rates. This really creates unbearable demands on the sensing devices, storage, processing devices, and communication systems that all have to deal with these large amounts of data. In fact, there are more than 3 million data centers worldwide just to store this data, like we see in this data farm center here in Finland. This also leads to extremely high power being consumed on acquiring and processing these large data sets to such an extent that the energy consumption of the IT industry is larger than many big countries such as Russia and Japan. By 2022, Cisco predicts that the internet traffic will approach a zettabyte. A zettabyte is actually 10 to the power of 21 bits, which is a huge number. So the question is whether we really need all of this data for the tasks we're actually interested in solving. What we claim in this talk is that there's a lot of redundancy in data that is not being exploited today. As an example, if we look at medical imaging devices, they tend to be large and bulky, they lead to high radiation, and they take a long time to scan. Now, this is because they acquire a large amount of physical data from multiple sensors, as we can see here, for example, in this plot coming out of an ultrasound machine. However, not all the acquired data is being used for clinical diagnostics. Rather, it is typically first projected down to a series of images, which has much less data than what was originally acquired. As another example, smart cities or autonomous vehicles collect a large amount of information from many sensors and cameras, which at the end is distilled to very specific decisions. Finally, if we look at deep neural networks, which we know work extremely well when they're trained on huge amounts of training samples, for example, when we do this for image classification, but we also know that children can perform classification tasks after seeing only very few examples. So these examples illustrate that we seem to be acquiring much more data than is actually needed for solving the tasks we're interested in. And this leads to the question whether we can acquire really only what we need. Girl in a digital world. So this song by Judy Gorman, who's actually a pop singer and not an engineer as far as I know, nicely captures the essence of sampling. Today, more and more of the processing is of course being done by digital devices. However, the world around us is analog, and therefore to enable digital processing, we first convert the continuous time signal into samples using an analog to digital converter. So what the sampler does is it first samples the signal at given points in time, and then it's going to go ahead and represent the sampled values by a sequence of bits using quantization. Now, the sampling rate today in essentially all ADCs follows the well-known Nyquist theorem that says that sampling should be at least at twice the highest signal frequency. In fact, data acquisition today is done in modular blocks. So suppose, for example, we want to acquire this radar image. Then what we'll do is we'll transmit and receive a radar pulse. The sampler will sample each received signal at the Nyquist rate, which in this case could be quite high if we want good resolution. The samples are next quantized, typically based on the well-known high rate limit that dictates that for each bit we add, we're going to gain roughly 60 dB in quantization SNR. The bits are then digitally processed, where only at this point is the desired task of the system taken into account. So for example, in the context of radar, we jointly process multiple signals, and the goal is to beamform the data to form a directional beam in a certain direction by applying adaptive weights. And after this processing, we obtain the output image, which is basically a projection of the continuous time data onto some low-dimensional space. So in the standard approach, as you can see in this description, each of the blocks in the acquisition chain is designed separately, and it's designed based on local optimality criteria that are relevant only to that block and do not take into account the other system properties or the overall task we want from the system. Now, this approach leads to high demands on the individual blocks, and in particular on the sampling and quantization rates. So today, of course, we use signals that have high bandwidth because we want to get a high rate of information and communication and better resolution, for example, in radar. But this means that the Nyquist rate and quantization rates are going to become very high if we don't take other properties into account. Now, high rates are very difficult to execute in practice in terms of hardware and power. If we look in the context of medical imaging, and in fact imaging more generally, high rates also translate to high scanning time and large radiation dosage. So these ADCs lead to many system bottlenecks. What we suggest in our work and in this talk today to overcome the data management issues is to change the way we design systems so that all system components are designed jointly and are not optimized separately. In the optimization, we're going to take into account both the desired outcome and also the structure of both the signals and the system. We'll see that by exploiting the structure and the task, we can substantially reduce the rate and also improve system resolution. In fact, furthermore, we can show that these ideas of joint design, exploiting the task and the structure, can also be used to develop model-based interpretable deep learning methods that nicely reconcile models with learning from data. So using this notion of model-based joint design, we'll show that we can develop a myriad of new systems, including compact imaging devices, joint radar and communication systems, efficient wideband sensing, cheap and high-resolution radar, efficient massive MIMO systems, high-performance, low-bit quantization. We'll see this also leads to super resolution with examples in microscopy and ultrasound. And finally, it will lead to interesting interpretable deep networks in both communication, radar, medical imaging, and many more. So here's an outline of the rest of the talk. We're going to look throughout the talk at exploiting structure, exploiting the tasks, and exploiting models, and try to illustrate throughout the talk different examples to communication and radar systems. So we'll start by looking at the structure and see some applications to ultrasound and radar. We'll then talk about exploiting tasks such as power spectrum estimation and task-based quantization, and we'll see applications to cognitive radio, super resolution, MIMO systems, federated learning, metasurface multi-antenna systems, and joint radar communication systems. And finally, we will see how we can use these ideas to develop interpretable deep learning methods. So we begin by considering how we can go from sampling to sampling or compressed sampling by exploiting structure. And what you see here on the slide are some of the systems we actually built in the lab following these ideas so that these are not just theoretical, but can actually lead to new systems. One type of structure that we looked at a lot is a multiband signal in which several narrow bands are transmitted over a wide bandwidth, but the carriers are unknown or changing in time. Now, of course, we can treat such a signal as band limited to Fmax and sample at the relevant Nyquist rate, but that would be wasteful because sampling at Fmax allows us to recover signals of this form that occupy the entire band, and we know that our signal is never going to occupy the entire band. The same model can be used in imaging, like in hyperspectral imaging or multispectral CT. Another model that appears in radar and ultrasound imaging, and in fact in any time-of-flight imaging, is the model of a stream of pulses. So this model was first suggested by Betterly and his colleagues in a beautiful series of works, which they refer to as finite rate of innovation. In this model, we have a stream of pulses, as we see over here, where we don't know the times of arrival or the amplitudes. This problem appears in radar, where in the context of radar, the reflections come from the different targets. Another important area where this model arises is in ultrasound imaging. An ultrasound image is actually formed in a very similar way to a radar scene. A known pulse is sent through the ultrasonic probe, and what we receive at the probe are reflections of the pulse as it propagates through the tissue. The image is then formed by identifying these delays in amplitudes. Now, it turns out that ultrasound is actually a much more difficult environment than radar, since it's very noisy and also near field. Therefore, in practice, within the probe, there are multiple elements, typically 256 elements, where the signals are received in all of the elements and then beamformed in order to increase SNR and resolution. This beamforming is done on a fine grid, which necessitates high rate sampling even beyond the Nyquist rate. So here the challenge is not only to reduce the sampling rates, but to do it in such a way that we can perform the beamforming on the low rate grid. Now, in order to achieve this, we introduced the notion of compressed beamforming, or more generally compressed processing, where we sample in such a way that the processing can be done at the low rate as well. So it's not only about reducing the sampling rate, but doing it in a way that we could do the processing at the low rate as well. In the context of ultrasound, for example, this leads to several clinical advantages that we're going to talk about later on. So, for example, we could decrease the size of the machine due to this. We could increase frame rate and increase resolution. We can pave the way to 3D imaging, and we can enable remote wireless ultrasound. We'll see a prototype of this later on in the slides. It turns out that all of these examples, and in fact many others, can be treated in a unified mathematical framework of a union of subspaces model. This model assumes that our unknown signal lies in a low-dimensional subspace, but a priori we don't know which low-dimensional subspace. So there are many options of subspaces, even possibly an uncountable number, and what we know is that our signal lies in one of them, but we don't know which one. The importance of this model is that we can show that the minimal sampling rate needed in the union model is the rate associated with the sum of two spaces in the union, irrespective of the number of subspaces. And this is the key result that paves the way to Sub-Nyquist sampling. So now we have a theoretical result, and the next step is actually providing an explicit hardware design that achieves this minimal rate. And this is provided by the framework we developed of sampling, which leads to concrete system design at this very minimal low rate possible. In order to reduce the rate, what we suggest is a counterintuitive idea, which is that we need to alias the data prior to sampling. Namely, we linearly combine all the possible subspaces into one low-dimensional subspace, and then we sample at a low rate. Now, in practice, the aliasing is performed by mixing with these periodic functions. And this is what you see here on the various boards that we actually developed in the lab. In the analog domain, we mix with these periodic functions. This is the analog pre-processing. We then acquire with low rate simple ADCs. And then in the digital domain, after we sampled, we're going to rely on ideas of compressed sensing in order to recover the underlying analog signal. What we're able to show is that this approach is actually optimal. This sampling hardware that you see over here is optimal under several different criteria. So from a sampling or mean squared error point of view, we can show that it achieves the Cramer bound, so it leads to the minimal error that can be achieved when sampling at a given rate. And from a communication perspective, we can show that it minimizes the worst case capacity loss for a wide class of signal models. After we sample using these ideas, as we said, we're going to rely on compressed sensing for recovery. And the idea is that we could locate the true subspace from these low-dimensional samples. So to do that, we rely on the idea of compressed sensing, which says that if we have a sparse vector, meaning a vector that could be very long, but has only a small number of non-zero elements, it could be recovered from a small number of measurements. So in our case, X basically represents the possible underlying subspaces, and we could recover the true active subspaces from our low-dimensional measurements. Now, in practice, in order to address many of the practical problems we're interested in, we have to extend compressed sensing in various different ways, for example, to nonlinear problems, to problems with tracking, and many other extensions. There's also been a lot of work on how to use deep networks to recover from compressed samples using various forms of learned structure. By combining the analog and digital ideas we just presented, we arrive at a general framework for Sub-Nyquist sampling, which is based on structure that can be applied to a wide variety of systems. So here on the slides, you see some of the prototypes we've developed based on these ideas, where in our books here on sampling theory and on compressed sensing, we go more into the theory behind these ideas in hardware. Next, we're going to turn to discuss applications and hopefully convince you that despite this very famous quote by Albert Einstein, in theory, theory and practice are the same, in practice they are not, if we actually take the practice into account when we develop the theory, then we can get these ideas to work in practice. So let's go ahead and take a look at some of the prototypes we've developed in our lab based on the ideas, where the first prototype I want to show is to ultrasound imaging. So we've been able to show that using the ideas we presented earlier, we can acquire an ultrasound image by sampling at only 4% of the Nyquist rate in every individual channel, and we also reduce the number of channels. This paves the way to some interesting clinical applications. So it enables 3D imaging that today is highly limited by the data rate. It allows high frame rate, for example, for cardiac imaging, because we could do the processing quicker. And finally, what I believe is the most exciting application is to a handheld wireless device that I'm going to show on this next slide. So today, ultrasound systems are big, bulky machines where you use a probe to transmit and receive the signal. And then the signal is transferred through a cable into the ultrasound machine, where only in the machine is the data sampled and processed. Now, the reason that the sampling is not done in the probe is because of the many elements and the high rate, so that you simply cannot do that high rate sampling within the probe. Now, using our Sub-Nyquist ideas, we can now sample within the probe. And the advantage of that is that, first of all, we get rid of the cable in the machine. So all we need now is a probe. The data is sampled, sent over any Wi-Fi channel, either to the cloud or to some imaging device where we could recover the image. The second advantage is that we now actually have access to the raw data, the actual RF signals that we receive in the elements, which we could then go ahead and process using advanced methods, rather than just having to process the output image. So
Hello,
what I want to show
everybody.
next is a prototype we've developed in the lab.
Of a normal heart.
Here's Dr. Shai Taiman Yilden, a cardiologist we're working with, who is scanning my student Regev. He is using the probe we developed. The data is going directly to a local machine, to a tablet, and to a remote machine via the cloud.
We can see the different structures of the heart.
The cable you see is just for powering purposes.
We can see the nice motion of the leaflets. We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
And now you see Dr. Shai Taiman Yilden scanning directly to the tablet. Now, one of the nice aspects of this wireless probe is that it enables access to data, which previously was simply not available, and this is the channel data. Now, this opens the door to many exciting new clinical applications that previously were not possible. In fact, we've begun a clinical forum dedicated to this topic with many leading clinicians in both Israel and in the Boston area, where we're examining various new clinical applications that are enabled by channel data processing. So this is a really nice example of how new technology can not only lead to more efficient systems, but could actually enable entirely new clinical applications by enabling new views on the data. We can, of course, apply similar ideas to radar in order to obtain compact and power-efficient radar systems. So next, I'm going to show a short video of some of the prototypes we've developed in the lab, and many of these ideas are summarized in more detail in our recent book on compressed sensing in radar, which was edited together with Antonia De Maio and Alex Chaimovich. So here's a short movie of some of the prototypes we've developed in the lab in the context of radar. And we know that in radar, we have some basic trade-offs between bandwidth and resolution. We have another trade-off between the dwell time and the Doppler resolution that we can achieve. And finally, the last trade-off we have is between spatial resolution and the number of antenna elements. So in order to break these trade-offs and gain in terms of resolution, we've used the sampling paradigm. And what you see here is the actual board that we've developed in the lab. And next, you're going to see how it works in practice. So we could sample at a very low rate by using only a small part of the bandwidth. We sample over these small narrow bands. And what we see over here is real-time processing, where you see that we still get very good resolution. So we look at targets in the presence of high clutter, high noise, and still you see that we could get very good range Doppler resolution, even though we're sampling at very low rates. Now, this actually paves the way to cognitive radar, where we could share the spectrum with communication systems, since now we said we're only using a small amount of bands throughout the bandwidth. So this means that we can now look at where we have vacancies in the communication channel and use a radar signal only in those bands and still get the same resolution. We can also use this to get better Doppler resolution by sharing pulses in multiple directions and being able to recover from these Sub-Nyquist pulses. So this allows us to recover several areas in the time we would usually only recover a single area. And here you see two maps recovered in the time we would typically recover only one map, but still getting very good resolution. And finally, we could get spatial subsampling. So instead of using a standard MIMO setup, we could further dilute it, use much fewer antenna elements, which of course reduces the RF chains as well. And still what we can show is that using our methods, we get very good resolution. In fact, we even get better resolution than the Nyquist approach because we use more sophisticated methods. So right now we're exploring applications of these ideas to automotive radar, where cheap, fast scanning and coexistence with communication channels is very important. So what you see here is a demo which we developed in the lab, and this shows the use of cognitive radar and low bandwidth radar for automotive systems. And what this enables is scanning several areas simultaneously while still communicating with nearby vehicles. Another important issue in real-world systems, and in particularly in complicated environments like automotive radar, is that the pulse shape often gets distorted due to unknown interferences. The standard Sub-Nyquist ideas we presented rely on the known pulse shape. So we extended our Sub-Nyquist results to the case in which the pulse shape is unknown by using ideas of blind deconvolution. So here in this demo over here, what we can show is that by using two antennas, we can perform blind Sub-Nyquist sampling and recover the target by still sampling at a very low rate and not knowing the underlying pulse shape. So here you can actually see a demo of a system that we've developed in the lab. This is the actual hardware that we use in the demo. And basically this hardware consists of two antennas, each sampling at a Sub-Nyquist rate. And by exploiting ideas of Sub-Nyquist sampling and blind deconvolution, we can still go ahead and recover the delays and Dopplers at very high resolution, even though we sampled at a low rate. So here you see the actual receivers that we've developed in the lab, and shortly you're going to see the actual results. So here you see the screenshot where we can get very good delay Doppler maps and very good resolution, even though we're sampling at very low rates and we're not assuming that we know the underlying pulse shape. Finally, the ideas of spatial subsampling can also be applied to antenna arrays for automotive radars. Although large antenna arrays increase resolution, they are very costly and drain the battery, which is a huge difficulty in automotive systems. By using the ideas of Sub-Nyquist sampling, we can develop methods to optimally sparsify the array and get the same resolution and direction of arrival estimation using a small number of antenna elements. In our hardware implementation, we actually use a deep network to choose the optimal elements in an adaptive fashion based on the target scene that we currently have. So here we see a short video of the prototype we've developed in our lab. Here you see the actual antenna, and here you see the field experiments. So we use this as outdoors in order to be able to detect several different targets and estimate the direction of arrival using only a small number of the elements in each run, where the elements themselves were determined by a deep network based on the current scene that was currently recovered. So here you see that the performance is really good. We could get very good resolution and better resolution than if we use just a random array selection. So what we're going to do next is turn to discuss how we can exploit the system task in order to reduce rates even when there is no structure in the signals. There are many applications where we sample a signal, but we're not actually interested in recovering the individual signal, but rather we're interested in some function of the signal. And what we want to discuss now are examples of how we can exploit these tasks to reduce sampling rates even when there's no structure in the signals, and how this again could be used to introduce some interesting new technologies. So more specifically, we're going to look at recovering the signal power spectrum, at the interplay between quantization and sampling, at tasks related to communication, such as channel estimation, and sampling sets of signals when we're interested in their joint output, like in beamforming for radar or ultrasound. So we're going to be begin by looking at power spectrum reconstruction, where we sample a signal, but what we're interested in is recovering the second order statistics of the signal. Now, this appears in many different applications in radar and communications, for example, in cognitive radio, where we only want to detect the support of the signal, in direction of arrival estimation, which is typically done from the covariance, and in other applications as well, such as microscopy, where we're interested in the brightness image, which is proportional to the variance. So the question we would like to ask in this context is, what is the minimal sampling rate when we sample a signal, but we want to estimate its covariance, assuming that the signal is Whiteson stationary and ergodic? Now, in the past few years, there have been several very nice papers that looked at this problem and considered very specific sampling mechanisms in the asymptotic regime. In our work, we take a more general approach because we want to be able to characterize general sampling sets and finite sampling rates. It turns out that substantial rate reduction is possible even for finite sampling sets that can be achieved with concrete hardware. So instead of going into the mathematics, which is quite involved, I'd like to try and give some intuition as to why sampling rate reduction should even be possible. So recall that what we're trying to do is to recover the covariance of a stationary signal, which we know is going to be a function only of the time differences. Now, suppose we have a sampling set, like this set you see over here, which is not very dense, and therefore it will not obey the Nyquist rate of the signal. So if we try to recover the signal, we won't be able to do that from this sampling set. But remember that all we want is to recover the covariance, which depends on the time differences. So even though this sampling set could be quite sparse, the differences, if we look at the difference set, meaning the differences between every 2 points in the set, could actually be quite dense. Now, since the covariance is estimated based on this difference set, if the difference set is dense enough, then we could go ahead and estimate the covariance. So we could, of course, make this more substantial from a mathematical point of view. We could derive explicit conditions under which sampling sets will be viable for covariance estimation, even though they're not sufficient for conventional signal estimation. But I'm not going to go now through the technical details. Instead, I want to give you some examples and applications where we can use this. So one of the applications that we've looked at is to cognitive radio. The idea in cognitive radio is to build smart radios that can sense the spectrum and discover channels that are not being used, even though the spectrum band is actually licensed. Now, if we can do this, it could allow to overcome spectrum congestion and increase channel capacity. There's many difficulties in employing cognitive radio, but one of the main issues is how to scan a wideband spectrum continuously with a cellular phone. Now, we know that using covariance estimation, we can actually recover holes in the spectrum, and therefore we could go ahead and apply this to cognitive radio. So what you're going to see now is a prototype that we've developed in our lab for cognitive radio, and in this review, you can find much more details to this application. So here's the actual board we developed. It samples at only 6% of the Nyquist rate, a sampling rate of only 360 megahertz, even though we're looking at signals of several gigahertz. So here you see the actual real-time operation. What you're going to see at the top are RF signals that are changing rapidly in time over a very wide spectrum. Here you see the aliased spectrum after this low rate sampling, which of course looks like junk, but using our techniques, you can actually go ahead and recover the signal and find exactly where it's located. Now, these techniques are very robust to noise. They don't depend on any specific properties. They can be used irrespective of the actual properties of the individual signals. And like I said, they work even when there's a lot of noise, as you see here in this example. An entirely different application that at first glance is unrelated to sampling is to super resolution microscopy. Optics is extremely convenient to use for microscopy. However, its spatial resolution is limited by half the wavelength used for illumination, which is known as Abba's diffraction limit. Therefore, when using an optical microscope, we can see, for example, cells, but not proteins and small molecules. In 2014, the Nobel Prize in Chemistry was awarded for super resolution using fluorescence microscopy. The idea is that to form a super resolved image, we take thousands of exposures, where in each exposure, only a small number of fluorophores are actually activated, so that the position of each fluorophore can be determined with high precision by simply localizing it. This leads to very high spatial resolution, but at the expense of temporal resolution, since now we need thousands of frames to form a single image. What we can show is that by using ideas of sampling theory, we can get a high-resolution image using a small number of exposures, where we use the fact that all we need is the variance of each pixel, since these are brightness images. We can therefore rely on our previous theory for covariance estimation that asserts that we can recover the image from fewer samples, which means reducing the acquisition time and paving the way to live cell imaging. Here we see some examples where we can use SPARCOM, our method, to recover very high resolution images using 2 orders of magnitude fewer measurements than we need for STORM, which is the method behind the Nobel Prize. We've also recently extended this method using a model-based deep learning approach, where we perform training from only a single simulated high-resolution image and can obtain better performance than SPARCOM without having to know any system parameters. We're now looking at using SPARCOM to investigate various biological processes, and in particular, we're collaborating with a group of Professor Biladaran in order to image T-cell receptors in live cells. We're also exploring using these ideas to improve ultrasound imaging. So in ultrasound, we can't rely on fluorophores, of course, but we could use the fact that today, very often in ultrasound scans, one uses contrast agents, just like is done in other imaging modalities such as MRI and CT. These are essentially microbubbles that are injected into the bloodstream, and when we image in a fixed plane, these microbubbles hit the plane in a stochastic fashion, very similar to the fluorophores that we've seen in optical microscopy, and therefore we can use the same method. This leads to very good depiction of the blood vessels, as we can see here in this image, and we're now exploring these ideas in clinical applications, such as early detection of breast cancer and monitoring of Crohn's disease. The next task we want to consider is quantization. We're going to show that the ideas we've discussed so far can lead to very efficient quantization systems, which will have applications in communications, in radar, massive MIMO, joint radar comm systems, and intelligent reflected surfaces, where here again on the slide, you see some of the low quantization systems we've built based on these ideas. Now, in general, sampling theory focuses on sampling in time, but not in amplitude, while rate distortion theory of Shannon coding theory considers quantizing the amplitudes, but assumes sample data. This raises the interesting question of what happens when we combine the two. Could we develop a rate distortion theory that takes into account both sampling and quantization? And most importantly, do we really need to sample at the Nyquist rate when we take quantization into account? In other words, since we're going to have distortion anyway due to quantization, maybe we can allow distortion due to sampling as long as it doesn't add to the total overall distortion. We were able to unite sampling theory and rate distortion theory and derive analog rate distortion curves, which tell us for a given quantization rate what the minimal distortion is on the analog signals. Now, once we have these curves, we can analyze them and determine what the minimal sampling rate is to achieve the optimal distortion for different inputs. So here we see an example where we have these 3 inputs that have the same bandwidth. This is the Nyquist rate for these signals, but we see that for the blue and red signals, we can actually sample way below the Nyquist rate when the bit rate is low. Now, what's very interesting is that we could take inputs that are not band limited, like this green input over here, and still for every given bit rate, we can find the optimal sampling rate, which is going to be finite. Now, in the results we've shown so far, in order to achieve these optimal rate distortion curves, we actually have to use vector quantizers, which are impractical to implement in standard systems. Actually, most ADCs rely on simple scalar quantizers that yield performance that are far above the rate distortion curves. So the next question we want to address is whether we can exploit the underlying task we're interested in order to simplify the quantizer. Namely, we want to develop hardware-limited quantizers that achieve the optimal performance by taking a specific task into account. So in the context of communication, we look, for example, at channel estimation or bit recovery. What we propose to do is to use simple scalar quantizers, but to allow for analog combining before the quantization. So we literally mix the input to be quantized, very similar to what we do in compressed sensing, but here we're doing this to reduce quantization error. What we're going to do is to jointly optimize the system, which consists of the combiner, the quantizer support, and the post-processing in order to minimize the error in various communication tasks. Now, it turns out that when we do this, we could actually use simple scalar quantizers and still achieve the optimal performance we would have gotten using vector quantizers. So this opens the door to very many exciting applications of task-based quantization, where we can allow for low quantization rates without losing performance in many different problems in communications and radar. As an example, let's look at massive MIMO communications. So we know that massive MIMO has been gaining a lot of interest for next generation cellular systems, where the idea is to increase throughput by using very large antenna arrays. Now, the downside is that this requires expensive hardware to sample, quantize, and process the data from all the antenna elements. There's been a lot of work that considered analog combining in this context to reduce the number of RF chains, and in fact, in some of our earlier work, we developed a general optimization framework that allows optimizing the analog combiner for different communication tasks. There's also been a lot of work on using low bit or even 1-bit quantizers in each RF chain. The typical approach is to apply a 1-bit quantizer and then try to compensate by appropriate post-processing based on approximating the resulting MSE. This, however, leads to performance loss. Now, instead, we could use our general theory to develop an optimized precoder to both reduce the number of chains and the number of bits. And what we can show, and you see here on this slide, is that by using this approach, we can approach the performance of the system with full RF chains and high bit rate. We're now exploring very similar ideas to MIMO radar, where we can use very low bit systems by introducing an analog combiner. Now, these systems require knowledge of the channel statistics in order to optimize performance. As a next step, we use deep learning to compensate for unknown channel statistics, but we do this in a model-based fashion, namely we keep the structure of the quantizer and learn the weights based on optimizing our task-driven metrics. So here we see a demo that we've developed in our lab for a low-bit system used in the context of channel estimation in a MIMO channel. And we're now using very similar ideas in MIMO radar. So what you see here in the demo is the analog combiner we've developed that allows using a small number of RF chains and a small number of bits, but still getting almost the same performance in channel estimation. In these demos, we use additional hardware for analog combining. An alternative to conventional RF hardware is to use metasurfaces for this task. Metasurfaces can change the radiation pattern based on changing the current that runs through them, and they've been used in many different applications due to their scalability and low power. Until now, metasurfaces have been considered in the context of wireless communications as passive reflecting devices, which can be used to shape the propagation environment and in that way provide cost-effective beamforming. In our recent work, which was led by Dr. Neil Schlesinger, a former postdoc in my group, we've been looking at using metasurfaces as active reconfigurable antennas with advanced analog signal processing capabilities for next generation transceivers. As an example, in the context of analog combining, we can use DMAs by simply varying the current to achieve different filter responses, and in that way easily implement analog combining with a low cost and low power solution. Not only does this allow to reduce the power and hardware size, but it actually provides better performance than traditional hardware because the metasurface leads to frequency selective filters. This is work we've been doing with a group of David Smith and Duke, who's an expert in metamaterials. We can also incorporate low bit quantization in the design, and in that way develop a metasurface MIMO receiver, which operates at low power, simple hardware, and very low quantization rates without harming performance. Because of this frequency selectivity of the meta antenna filters, we can use this also for wideband signaling. So combining our task-based quantization theory with these meta antennas leads to practical, very high-performing low-bit quantizers for many different applications. Until now, we've seen that we can reduce the rate, the size, and the power in both radar and communication separately. The next step is to see if these savings in resources can be combined. Now, this is particularly useful for joint radar communication systems, which is an emerging topic that is important in self-driving cars, which constantly assess their environment. They do that by having both wireless communication transceivers and multiple sensors, including automotive radars. So this motivates designing these functionalities in a joint manner, and this can lead to substantial gains in size and cost and power consumption and in overall performance. In a recent review paper we published, we reviewed various forms of joint radar communication systems that have been proposed in the literature. The first is having two separate waveforms that do not interfere with each other. The second is using a COM waveform for both radar and COM, for example, by developing OFDM radar. The third is designing a dedicated waveform that is good for both radar and COM. And finally, the last approach is to embed communication bits in a radar waveform. So here we're going to focus on this last idea, which has some nice applications and methods. So the main idea is to send a radar waveform, but to do it in such a way that COM bits are embedded in it. And in particular, in our work, we're looking at index modulation, where the indices are embedded in which frequency and which antenna element is chosen. So we'll see that this leads to really good performance of the radar while maintaining very good performance of the communication system. So the first approach we're going to suggest in this context is what we call major COM. And here we use an array of antenna elements to send frequency modulated radar waveforms. The COM bits are embedded in which antenna is chosen and which frequency is used. What we can show is that in this way we get perfect radar performance as if we use the entire array and still get very good COM performance. The disadvantage, of course, is that we're still limited in the COM rate. So what we suggest next is to extend this idea by allowing for higher communication rates by using some of the antenna elements for COM and some for radar, and we do that by using two separate waveforms. So here on the slide, you see an implementation of both of these systems that we did in the lab. So in this video, you see the demo that we've developed in the lab for these joint radar communication systems, and on the slide, you see the actual hardware. A final application of task-based quantization is to federated learning. The idea in federated learning is to train algorithms using multiple decentralized devices without sharing the local data. So what's actually shared is only the weight updates of the deep networks. This enables both efficient learning and also ensures privacy since no data is actually shared. However, of course, the communication costs in sharing the weight updates could be quite high. So what we suggest is to quantize the weights for the task of learning. And what we can show is that we could quantize down to a really low number of bits, even 1 bit, while still obtaining the overall learning performance. We can also combine these ideas with those of precoding and analog combining. If we send the signals over an analog channel, we will get natural combining thanks to the channel. We could then properly precode the signals to boost performance and develop a federated learning approach that for the first time can be shown to be convergent to the local solution, even in the presence of noise. So now I'd like to end the talk by discussing briefly how one can combine models with learning in a systematic way. Now, we're all aware of the fact that today a very popular approach across all data science are ideas based on learning that learn the information needed from large amounts of training data. With enough data, deep networks tend to learn almost everything and have led to the best results in various tasks like image recognition, speech translation, and many more, which do not have good models. However, there's still many challenges with deep networks. In particular, we need very large training sets. It's very hard to interpret the results or to learn mechanisms using these results, and large data sets are needed for training, and it's also very hard to say much about generalization and robustness. On the other hand, if we look at signal processing, it is in general based on physical models. This allows us to easily incorporate domain knowledge and structure into the method. It also enables inference with small data sets, and it's easy to assess the quality of the output. The main drawback is that traditional signal processing relies on accurate model knowledge, and in addition, the inference can actually be quite slow. So the question is whether we can combine the ideas of models and structure that we talked about until now with deep networks to get simple, efficient, deep learning methods. To see how we can do that, let's take a bird's eye view on signal processing versus deep learning. In standard signal processing methods, we usually have a set of measurements, which we're going to call Y, from which we want to infer some unknown, which we're going to call X, and then we typically have a model that relates Y to X, which in this case is going to be this function g of x. And then we use that to design an algorithm that is going to determine x by optimize some metric, denoted here as f, which relies on the measurement and this known relationship. Now, if we try to optimize this metric using some iterative approach, it will typically lead to a series of steps that have to be carried on the input. And these steps will consist of some mathematical operation, some iteration, which will depend on this knowledge of the model, and then some post-processing. Now, on the other hand, if we look at what happens in deep learning, we don't assume we have a model, but instead we perform magic in some sense by replacing the model by a black box that does not know anything about the problem, but this black box is going to obtain lots of inputs and paired outputs, and from them it learns the parameters in this network to form a deep network. We then apply this learned network to a new input y to obtain the recovery x. So to combine these approaches, we're going to suggest two methods. The first is to integrate model-based methods into deep learning by relying on the very nice idea of unfolding first suggested by Gregor and LeCun. The second is to actually do the reverse, to integrate deep networks into existing model-based algorithms. So let's first look at this idea of unfolding, which was suggested by Gregor and LeCun. To use this approach, what we do is we go back to the iterative algorithm that we've seen before, and we explicitly write out, let's say, t iterations, or for example, 10 iterations, a small number. So up until this point, all we did was write out these iterative steps, but in the final step, what we're going to do is we're going to free some of the parameters in this iteration, meaning the model parameters that are not known, we are going to free and learn them from training data. So this leads to a very powerful class of unrolling methods, and those of you interested could see a recent review that we wrote on this topic. Now, we've applied this to many different problems. Let me just briefly mention, we've applied this to blind deblurring and got better than state-of-the-art results using much less training data. We've applied this to super resolution, for example, in ultrasound. We've applied this to separating tissue from blood by modeling the blood as sparse and the tissue as low rank, and then unfolding the resulting optimization problem. We're actually now exploring using the same idea to clutter separation in radar. Now, at the time, we called this method Corona, Convolutional Robust Principal Component Analysis, and it looks like since this method has actually gone quite viral. The last approach we suggest is taking an existing model-based algorithm that is known to perform well and simply replacing any block that requires model parameters or is difficult to compute by a deep network. Now, we've been applying these ideas to many problems in communication. So one example is for simple decoding over unknown channels, where we based our deep network on the Viterbi algorithm, and this leads to what we call a Viterbi net that has the same structure as the Viterbi decoder, but allows to adapt to unknown channels. Here we see an implementation of the Viterbi decoder, where we can show that it is able to track channels over time, even though we don't know them. So you see here that the performance that we get from the Viterbi net is continuing to be optimal, very low bit error rate, whereas other deep learning methods, and of course the Viterbi decoder itself, the performance degrades as the channel is varying, since it is built upon a nominal channel model that is not going to hold throughout the communication cycle. We can also generalize these ideas to general factor graph models and perform message passing over unknown graphs by learning only the graphs from training data. Finally, another example is to interference cancellation, which is very popular in multi-user MIMO communication networks. And we've used this in a very similar way to develop a successive interference canceller that does not have to know the actual channel information. To conclude, we introduced a framework for interpretable, efficient, and high-resolution sensing by relying on exploiting structure in the problem and the actual processing task in both model-based and data-driven methods. And we do this by performing joint optimization of all system components. We saw that this leads to new mathematical theories that provide bounds on sampling and resolution. We talked about new engineering developments leading to new technologies. And in the future, we hope that this combination of mathematics and engineering will lead to new scientific discovery and new clinical methods by seeing information that we haven't seen before and by tracking effects faster than is possible today. So throughout the talk, I skipped through all the mathematical details. You could find them on our webpage and in our recent books on these topics. Of course, none of this would have been possible with my amazing lab team, the dedicated students, postdocs, and engineers that I've had the privilege and honor to be working with over the years. And of course, my amazing collaborators who have contributed greatly to all these ideas that I presented today. So let me end by thanking you for listening to me and wishing health to everyone in the community.